Okay, thank you very much. My name is Nosikov. I'm from Kaliningrad, and I and my colleagues present a talk about simulation of tsunami propagation by ray tracing method. Our motivation to construct the new numerical model that can provide fast and efficient calculation of main parameters of tsunami waves. What is the parameters? It's travel time from the source to desired endpoint, and amplitude of the wave. Earlier, algorithm for numerical analytical modeling of tsunami waves was presented in works Rakotov and co-authors. This approach provides fast and efficient calculation on main parameters of tsunami waves and consists of two steps. On first step, we have to solve Hamiltonian system, this traditional ray tracing approach. On the second step, we use a asymptotic formula for wave field. This formula based on canonical operator of Maslov and use the minimum information about the tsunami wave and provide fast and very accurate calculation of main parameters. And we can just estimate the amplitude of the wave. And we can illustrate this approach. On this slide, you can see illustration of two steps. The first step is just the traditional ray tracing. And then after ray tracing calculation, we can reconstruct the front of tsunami wave. And when we reconstruct the rays and front, we can use the previous formula and simulate the amplitude of tsunami wave, as shown on slide. Our motivation to provide, as I said, a fast and efficient approach. The most time-consuming, the most time-consuming approach is shooting method. On the first step, we have to solve the boundary value problem to calculate the ray between two endpoints. And we have to, previously we have to use a shooting approach. But this approach in nonlinear case is often unstable and requires considerable computational costs. That is our motivation to find alternative approach to shooting method. Alternative approach can based on variational principle of stationarity of travel time. For example, we can just write the functional of the travel time and construct variational equation. As the first step. The another step, we can use the direct optimization of the functional. This kind of approach used in different field of science, for example, in seismology. This approach, I mean, variational approach, direct variational approach, is already used for seismic ray tracing. In radiophysics, there are a few examples of application of direct variational method. Now, in current work, we want to demonstrate how direct variational method can be applied to tsunami propagation problem. On this slide, you can see the statement of the problem. We just you can see the expression of the functional of the travel time t. Then we just write Fermat principle as a principle of stationarity of travel time, and then the problem reduced to find all stationary points of this functional. In practice, how does it work? We have a boundary problems, for example, endpoints A and B, and we have to start from some initial approximation. For example, it could be absolutely random trajectory, and then disturb this trajectory in order to satisfy Fermat principle. So we construct iterative procedure in order to find all stationary points of the functional travel time. And then we just rewrite the functional travel time by the trapezoidal rule and minimize it. Just use the anti-gradient, negative gradient of the functional. As I said, we need to find all stationary points. In practice, we know that not only minima satisfies the stationarity, we have to also find the saddle points. And here, in order to find the local minima, we use a direct minimization of the functional. And in order to find the saddle points, we need to use multiple numerical methods to find saddle points. Just at first, we'll discuss how we search the minima. We just procedure of finding minima based on negative gradient, as I said previously, and we can just make it more efficient and more fast by two steps. At first, we use a force projection. Just we exclude tangent component of a negative gradient of the functional in order just to make the algorithm more fast, more rapid. And the second step, use elastic forces between intermediate points, which describes the ray trajectory. This elastic force controls distribution of points along the path. In order to find saddle points, we need to estimate not only first derivative first order, we need to calculate the Hessian and estimate the direction of increasing and decreasing our functional. Then we calculate the eigenvalues and eigenvectors, and then we just can invert the saddle points to the local minimum. And when we do it, we just use already known procedure to find the local minimum. And I would like to just demonstrate how to direct variational methods works to find the minima and saddle point. For example, we have this model situation in homogeneous two-dimensional medium, and we want to find all rays which between endpoints. Our optimization, we start from the straight line and then provide systematic identification of the minima and saddle points. At first, we start from the straight line and find the first minimum. This trajectory describes the first minima of the functional, and then start to find saddle points. And now we find the second solution of the boundary value retracing problem and go further and find the third solution. It's also a minimum. And then go back to the already known solution and check the another directions to be sure that we find all rays, that we're sure that we solve the multipassing problem. As a result, here we find 5 solutions. 3.1 is the minima, of functional and two solutions are saddle points. There is another illustration how does algorithm works. We provide modeling in Seamount model, just only one homogeneity, the center, and we can see that this situation provides three solutions: two minima as a green race, and one saddle point of first order by the violent clock. On this slide, you can see comparing between two approaches. On the left side, you can see the traditional ray tracing with different reflection angles and reconstructed fronts. On the right side, you can see results of calculation by variational method. The endpoints, endpoint B, systematically fixed on a different position, and calculate all rays. And also, it provides reconstruct the wave front. As a result, we can see these two approaches is absolutely identical, and we can use the variational approach in other simulation. There is another example, simulation in underwater ridge model. Here we can see the more complex picture of the rays and more complex picture of the wave fronts. On the left side, you can see results of calculation by traditional ray tracing, and the right side you can see application of variational method. It should be noted that this example has multiple caustics, and these caustics provide existence of stationarity of higher order. I mean, when ray just touch caustics, the saddle points invert to more high order. The first, for example, ray which is considered to minima become at first saddle point of first order, then second saddle point of second order, and higher. And here we just apply our new techniques of finding higher order saddle points. And here we can see that this procedure works fine. We can also, using a variational approach, we can also reconstruct such situations. And after modeled example, we try to check how does this method, our approach works in real situation when we have a real ocean depth, and we try to compare different. For example, just calculate the event March 11, 2011. It is Tohoku earthquake and Tohoku tsunami. The source located here, as you see in the picture, and we calculate for two stations. Calculate the travel time of two stations by two methods: traditional ray tracing and the shooting method, and new variational method, and compare it with the experimental data. Here we can see that all the methods provide a good results, and we have a good agreement with the experimental data. But this in the table you can see time of arrival of the tsunami wave in hours. For two stations, we can see the good agreement. And also, if, just in order to apply our ray tracing techniques, shooting approach, and also variational method, we have to smooth our real data, and we provide a special approach for a situation and smooth our grid. Below you can see the reference to the work where these techniques of smoothing the real data is described in detail. And now we just consider the far field station DART. It's approximately 8,000 kilometers from the source. On this slide, you can see results of simulation and the two pictures. On the left side, you can see the fronts reconstructed by the traditional ray tracing, and on the right picture, you can see the rays calculated by and by variational method. Both methods provide absolutely identical results. Here we can see the 5 rays, and in the table you can see the information about these rays, the number of the rays, the type of each ray calculated by variational approach, and we can compare the travel time calculated by two methods. And we can see that the difference between two methods is approximately 1 minute, which is where, in our opinion, very good agreement between two numerical methods. Conclusion: a new variational methods for calculating ray trajectories on tsunami waves with specified boundary conditions present. The variational approach allow to determine rays of different types, the minima and saddle points, and also I described the global optimization algorithm that provides efficient solving of boundary value problem and multipassing problem. On modeled examples, we compare the shooting method and variational method, and we obtain the absolutely identical results. The main advantages of the method is fast calculation. Each ray calculated less than 1 second. So in future, we can build a real-time numerical model that can provide travel time estimation of tsunami waves, the amplitude of tsunami waves, and this model will calculate the local parameter of tsunami waves and do it very fast and accurate. So that's it. Thank you very much.
Thank you very much. Are there any questions?
Yes.
Professor.
Yes.
Okay.
Hello. Yeah, this was very interesting. I wanted to ask you. You calculated the times and you found the methods are quite accurate and they coincide, etc. Have you ever tried, or is it possible for you to be informed about a tsunami and be able to run your program in real time? I assume it must be a tsunami that takes many hours, and so you can calculate with results before the tsunami reaches that beach, or somewhere good. Have you ever done this? Is this realizable? What do you think?
Yeah, we hope that in future we can construct this model. Now it is this work in progress. We just build the program scripts now and debug the problem, the program. But in future, we hope and work with the geophysics boss just to provide, as you said, a real-time model. Yes, because it is more interesting, because in such approach we don't need to calculate the wave field in the whole sector.
Yes, I understand. Now that's fine. Yes, I understand. Now, have you ever heard the name Sinolakis? Konstantin Sinolakis. It's S and Y Nolaikis.
I can ask him, maybe. I cannot. I can tell you. Yes, we know, of course. It's but yeah,
okay.
But
you do know, because he was recently received an award from the Japanese Scientific Society. He was very, very good. I know him well in Greece, and very well known in actually studying mathematically, as well as observationally, being able to understand when the tsunami will arrive, etc. So I would advise you, you are in contact with him, you know him, he would be interested to hear your results. You may even mention my name, Buntis, that I suggested him to you, and just write to him and see what he thinks, because he's a well-known figure in the Academy of Athens. Okay, very good.
Thank you for advice.
Thank you. May I make also a comment? Thank you very much for your suggestion. But we have very good connection with the people who works in tsunami in Russia, also in other countries. For instance, with Pelenovsky, who is a very close friend of mine, and so we discuss with him and with many people who are around him these problems, and so we, of course we will.
Good.
Yes, but there may be some small comments, because it's what we are really do. It is the localization of the tsunami wave problem. We don't work with the all waves, all tsunami wave, just the wave which is interesting in the point of observation. You see, it is not necessary to solve all the problem for the tsunami wave problem for wave equation everywhere, just in the neighborhood of this race. So that is why it is some parallel calculations and so on. And then all of they think more or less new, you see, so because it's a big program and it is in a progress. But thank you very much for your suggestion.
I understand.
Okay, let's thank the speaker one more time.